This is another very great example as it demonstrates the use of 3D finite element simulation software. The case which cannot be easily reduced to 2D without losing this terminal connector part. In this case, the primary winding consists of litz-wire and the secondary winding consists of solid planar conductors connected together in parallel. In this case, as usually, we will start with defining a domain type. This is going to be a symmetric problem, and for simulation type we are going to use a harmonic simulation because we assume that both primary and secondary are driven excited with a sinusoidal currents, and the heat is solved using steady state. Under the materials we choose core materials and conductors and dielectrics and copy them to the local materials that are being used in the simulation. Under the ferrite we have a material with defined conductivity as well as constant permeability. We need to be very careful by not exceeding saturation of the core, in this case ferrite. If we see that the magnetic flux in the core exceeds the saturation, then it's advised that we switch from relative permeability to B-H curve. But in this case we only have constant permeability. Core losses are defined as the Steinmetz coefficients. In this case there's no data table, so those Steinmetz coefficients are taken from some reference values. And for the thermal, those are general settings for the ferrites defined for calculating the heat conduction. For the copper, we defined conductivity and temperature dependency of this conductivity. Under the thermal settings, copper is a very good conductor, so we add its conductivity here as well. Under the core section, we create one core set by clicking on new group, then edit this core group. Here we use ER core shape type. As you can see, this ER core has those round faces, but by applying the right E parameter we can make them flat. So, and in TRAFOLO we do have a wide variety of different core shapes that we take from open magnetic, and you can almost all ferrite types define them using those default parametric geometries. So just by putting those parameters and clicking apply, you will get this core shape. Further, by choosing virtual gap, we will add a permeability gap between those two core pieces, but instead of making a physical gap, in this case it's just a slice, it's a phase boundary condition, internal boundary condition that will apply reluctance boundary condition for the magnetic field to pass this boundary. Next we move to the foil, to the coil section. We have 4 layers of litz-wire. Each layer is built as a pancake geometry type. Here we tell that the wire type is stranded litz, and there is 1 turn per each solid geometry. Even though there are 3 turns, because we have 3 separate geometries, we tell the software that each one consists of 1 turn per solid. Then under configure wire, here we just define our AC/DC coefficient. In theory we could also use homogenization in this case because this is harmonic simulation, and defining the fill factor of strands of conductive material within the wire. The most interesting is this complex shaped planar conductor, secondary winding. This is imported geometry. This geometry first was created in external CAD tool, and then we import it by clicking import, selecting the geometry, like in this case, like this one, and then after importing this geometry, you can specify that it is going to be a massive or solid conductor. You see there are other two types, stranded litz and foil. Those are special cases where we use homogenization, but because this one is built out of solid conductor, we want to resolve skin and proximity effect as is, so we choose massive. Next we move to the other section. Here we define the heatsink. For the heatsink we have special heatsink geometry type. All you need is just to adjust its location and translate or rotate accordingly. Also pay attention that because of this secondary winding, we slightly rotated our component by 90 degrees, so the symmetry plane goes not like this as usually, but like this. Next we go to the bobbin section. Here we just create a very simple brick that will act as a potting material between windings. Under assembly we need to assemble geometry, and this assembly step is going to cut our geometry by symmetry plane and specify geometry types and materials accordingly for each part of the component, and it's going to happen automatically. This is our component, and we can enable air and see the component within the air box computational domain. Next we move to the LMAC section. Here we are going to define the excitation for primary and secondary. Both primary and secondary are going to be excited with a current. Those current values are either taken from some circuit simulator or from estimates, and you can see those are, if we switch to the terminals, we can see that for litz-wire we have positive and negative terminals for each geometry, one positive, one negative, while for the solid conductor we specifically created this one terminal just to connect the solid conductor, and this will act as a positive terminal, and then we will have three negative terminals, and the software will know that those terminals they do have another symmetrical part of the component. So the voltage and the current will distribute accordingly, as if this would be like a full geometry. Here underneath we need to define the primary and secondary windings accordingly for each of those geometries. Next we move to the circuits. Those are default circuits, we don't need to modify anything. Here we see that both the primary and secondary will be driven by the current. Under the waveform we tell the software what is going to be the frequency, the primary current and the secondary current. In this case both currents were estimated by doing some hand calculations, but this could be also your circuit simulation, or if you don't know currents, then of course you can apply either voltage or current on the primary side and impedance on the secondary side. One thing that is very critical and very important to pay attention to, as we set both primary and secondary currents positive, we need to apply some phase shift between primary and secondary. This phase shift, 179 degrees minus, just tells us that both primary and secondary in the component will flow in opposite directions. In transformer, primary and secondary currents flow in opposite directions that cancel out the magnetic flux. So this is very important. There's of course another way how you can set up the direction for the current in primary and secondary is by changing switching terminals. But in this case the easiest and probably the most easier to interpret is this phase shift defined under the fundamental frequency. Next we move to the heat transfer section. For this component we assume that its steady state temperature is going to be 50 degrees. After the first iteration we can always modify this value later. This temperature is going to be used to adjust to correct the conductivity of the copper material based on the material properties. For the entire component, we will set external temperature as 20 degrees, so it's relatively cool air is going to be blown with a small forced convection. For this we will also set 20 watts per meter square per Kelvin, and let's assume that the component itself is placed on some board that efficiently removes the heat from the component. So instead of 20, let's put 50 degrees watts per meter per Kelvin. Next, we will head to the mesh. If you don't see geometry in this mesh section, then you need to click on the evaluate mesh. In this case, evaluate mesh was done automatically, and here, considering that we have solid conductor on the secondary side and we have relatively high frequency, we need to do some math. In this case, we will do some calculation for the skin depth. In this case, for 100 kilohertz, the skin depth is about 0.2 millimeters. Because we are solving a secondary winding as a solid conductor, we need to apply boundary layers on it to resolve the skin effect. In this case, total boundary layer thickness, we will start with 0.2. In further iterations, we may need to adjust this thickness slightly higher, and the number of boundary layers. Now we will use one layer, but in further iterations, further simulation runs, you would want to increase this number of boundary layers to better resolve the skin and proximity effect. All max element edge size, in this case, we are going to set 2 millimeters. This is just a very rough number for now to get the simulation running. And for this litz-wire, we already know that the diameter of this wire is roughly 2 millimeters, so we are going to apply 1 millimeter elements on those wires. This mesh is computed in less than a minute. It's relatively coarse mesh, but it's sufficient for our first simulation runs. Pay attention that here we can see boundary mesh elements applied on the solid conductor. Those will allow us better resolve skin and proximity effect. Next, we move to the solve section. The solver software recommends us using 5 cores. In this case, I will run on 8 cores. We will generate simulation setup files and then run the simulation. Once the simulation is over, we get this beautiful temperature distribution gap, but let's first move to the summary. As usually, we get loss distribution for primary, secondary windings, the core loss. We see that the most losses come from the windings, but there is also the core loss relatively high. Very low losses in the heatsink because there's very small gap between those core parts. For the magnetic flux, we can see that the maximum amplitude is 0.1 teslas. This means that this ferrite material is far from saturation, so we are safe to use constant permeability. For the coil losses, this is very interesting. Because we have this extended terminal for the secondary winding, there seems to be some current crowding happening here in this area, so this is something that we need to pay attention and make sure that this is what we actually get in real prototypes. But pay attention to those faces here. This is clearly a proximity effect. The current that is going in this direction then goes and returns back on another side of the planar, this conductor. They're in opposite sides, so they do attract each other. So there's clearly some proximity effect and additional resistance and losses generated here. So if we would want to optimize this component, we might consider maybe making this gap between those two slightly further apart. Also, we can see where are those losses generated in the heatsink. As mentioned before, the losses in heatsink are very small, but we can see where those are mostly where there's some leakage magnetic flux going outside the core. Core losses, as usually, are concentrated in those inner corners, and the temperature distribution, we can clearly see that windings that are encapsulated, they are running the hottest. The heatsink that covers the core effectively, efficiently removes the heat from the core part. So if one would need to optimize this component and make sure that it's reliable, then one would need to pay attention to the litz-wire, especially the one which is closest to the center of the component. So, as you can see, this is relatively fast and simple simulation in 3D FEM software. So try yourself. It takes just half an hour to set this model and run it.